In this video, I'm going to look at how to solve first-order linear differential equations using the integrating factor method. But first, however, I'm going to consider initial conditions. So I've looked at differential equations already, but previously we've had some unknown constant in our solution. For example, we might have y equals c times e to the power x. So we've got some constant coefficient of this exponential function. This would of course be the solution to the differential equation dy dx equals y, or dy, which is equivalent to dy dx take y equals 0. If we only have the differential equation, we can only find the solution up to this constant. So c is some constant. If we are also given an initial condition, for example, at x equals 0, or any condition, doesn't have to be initial, but some condition specifying a y value for a given x value. So at x equals 0, y equals, say, 5. Right? Then we can not only get this general solution to this differential equation, but if we have this condition, we can actually find out what this unknown constant is. And then we'll have some precise solution to this initial value problem involving both the differential equation and the initial condition. So if x equals 0, y equals 5, we can just substitute that into this solution to the differential equation, this general solution, and we'll get 5 equals c times e to the power 0. Now e to the power 0 is just 1, so that gives us that c equals 5. So this is equivalent to 5 equals c times 1, or in other words, c equals 5. So the solution to this initial value problem involving both the differential equation and the initial condition is going to be y equals 5 times e to the x, where 5 has replaced this unknown constant c. Solving another differential equation, say this one, dy dx equals 3y, we would get the solution y equals some constant c times e to the power 3x. If we had another condition on this problem, that say at x equals 0, y equals 2, then we would get, by substituting in 2 equals c times e to the 3 times 0. E to the power 3 times 0 is just e to the 0, which is 1, so we'll again get 2 equals c times 1. In other words, c equals 2. So in this case, we will get the general solution of the differential equation was c equals e to the 3x, and with this initial condition, we get that the c is 2, so that in the end the solution will be y equals 2 times e to the 3x. Moving on now, if we're given a initial value problem involving both a differential equation, say dy dx equals x times y, and an initial condition at x equals 0, y equals, say, 10. Okay, so now we've got an initial value problem involving both a differential equation and an initial condition. Well, I suppose the term initial condition would really tend to indicate that the independent variable was time, which might not be the case here, but in any case, I'll still use the term initial condition. So to solve first, we have to solve the differential equation. So you'll see this is a separable first order differential equation. So like before, we should divide through by the function of y, which is just y itself. I want to make a point here I didn't cover in an earlier video. Equal x. Okay, now when I divided through by y, we are assuming here that y is not equal to 0, because you can't divide by 0. The solution y equals 0 is in fact a solution to this equation, because if y equals 0, then dx will also be equal to 0, because the derivative of 0 is just 0. So we'll get 0 equals x times 0. So that's true for any x. We have 0 equals 0 for any x, right? The equation holds. In other words, the equation is, if we have, I'll just write this over here, 0 equals x times 0, then that means that 0 equals 0 for all x, right? So in other words, the solution, the y equals 0 is indeed a solution. But by dividing by y here, we're assuming that y is not equal to 0. Okay, so here I'm considering the case where y is not equal to 0, but in fact y equals 0 is also a solution. It's not the only solution, but it's a solution. Okay, so I'll continue to solve this differential equation by the same technique as before, using the separable differential equations technique. Well, I've already separated, so we can just integrate through by integrate with respect to x. So and that then becomes the integral of 1 over y with respect to y. And we can integrate this, and we'll get an integrating constant. So now we have that log of the absolute value of y equals x squared over 2 plus c, where c is some unknown constant, and we can write c is an element of R, which is a real valued constant. Okay, so then we can just take exponentials of both sides. Now this expression here, e to the power x squared over 2 plus c, can also be written as e to the c times e to the x squared over 2, e to the power c times e to the x squared over 2. Now this e to the power c is just some constant in itself. It's a positive constant because it's a e to the power of some real valued constant is necessarily positive. So we can just call that, say, k times e to the x squared over 2, where k is greater than 0. But we also note that we've got an absolute value sign here, so we can just write y equals plus or minus k e to the x squared over 2. Now, by writing plus or minus, this allows both a positive or a negative k, or sorry, a positive or negative coefficient. So we could call that, say, a e to the x squared over 2, where a could be greater than 0 or less than 0. And if we're only considering this solution, then it can't actually be 0. But remember before we had that y equals 0 is a solution to the differential equation. So we can actually say that we can allow a to equal 0, right? We could have restricted a here if from this statement here that y equals plus or minus a positive constant times the exponential function of x squared over 2. You would only get positive or negative coefficients here. Right, so plus or minus k cannot be 0, but I'll allow a to be 0 because if a equals 0, then we get y equals 0, which is actually a solution to the differential equation as I showed before. So a can be positive, it can be negative, or it can actually be 0 as well. So we can just write a is an element of the real numbers. A is a real valued constant. Now we've solved the differential equation. We've found that y equals a times e to the x squared over 2. So that's the solution to this differential equation, dy dx equals xy, where a can be any real value constant. But we also had this initial condition at x equals 0, y equals 10. So we can just substitute that in to our solution. So y equals 10 at x equals 0, so that it gives us that 10 equals a e to the power 0 squared over 2, and e to the power 0 squared over 2 is just e to the 0, which is just 1. So we get 10 equals a times 1, and therefore a equals 10. So the general solution to the initial value problem, dy dx equals xy and x equals 0 gives y equals 10, is y equals a e to the x squared over 2, and now we've found that a is 10, so it's y equals, the solution is actually y equals 10 e to the x squared over 2. It's the solution to the initial value problem, including both the differential equation and the initial condition. So that is y equals 10 e to the x squared over 2. That's the solution to the whole of the problem, which includes both the differential equation and the initial condition. So the solution to that problem is y equals 10 e to the x squared over 2. If we'd had some other condition, say for example at x equals 3, y equals 7, so some other condition, then we could have substituted that also into the solution to the differential equation, which would have been given us 7 equals a e to the 3 squared over 2. And now we don't have e to the power 0, we've got e to the power some non-zero number, which is actually 3 squared over 2 is 9 over 2, so that's yes, 9 over 2, or 4.5. So this means that a equals 7 divided by e to the power 9 over 2, or 7 times e to the negative 9 over 2. So we can see we don't get as neat a solution if we have a non-zero value in our initial condition for the independent variable. So if we had, when we had our initial condition being something involving x equals 0, y equals some other number, up here, at x equals 0, y equals 10, or whatever it might be, we got a neat solution that was just a was in fact 10, that value of y at x equals 0, which will work whenever we end up having the exponential going to exponential of 0, which is 1. So then this term just vanishes and we're left with the y equaling the a, whatever that, or the a equaling that value for y at that x equals 0, if indeed we end up having this exponential going to exponential of 0, which is 1. So if we had this other more messy case, so to speak, we'll get a bit more complicated looking solution. 7e to the negative 9 over 2. And remember, this is still some constant. It's an exponential of a constant, which is itself a constant. So it's just a constant times our exponential of x squared over 2. So again, our coefficient now, our constant coefficient now, a, is now 7e to the negative 9 over 2, because we had this condition. We could also write this as 7e to the x squared minus 9 over 2. So enough of that. Now I'm going to consider solving first order linear differential equations using the integrating factor method. Okay, so first order linear differential equation might be, say, dy dx plus 3 over x y equals say cos of x. Okay, so the integrating factor method involves finding an integrating factor, which will be some antiderivative of this coefficient of y, or this function in front of the function of x, which is in front of y here. So if you remember, a first order linear differential equation can be written as dy dx plus f of x times y equals g of x. Now, what we're looking for is an antiderivative of this f of x term. So we're looking for an antiderivative in this case of 3 over x. Now, an antiderivative of 3 over x is 3 times log of x. Now, we find our integrating factor by taking the exponential of that antiderivative of the f of x term. So it'll be e to the power 3 log of x, which is e to the power log of x cubed which is just x cubed. So our integrating factor is x cubed. Okay, this is our integrating factor. So what do we do? Well, we multiply both sides of this equation by our integrating factor. So that gives us x cubed times dy dx plus 3 over x times x cubed times y equals cos of x times x cubed. So we can tidy that up a little bit, and it will just be x cubed dy dx plus 3x squared times y equals x cubed cos of x. Okay, now, once we've done this, we will be able to write the derivative with respect to x of y times our integrating factor, x cubed, right, will be equal to this left-hand side. So, using the product rule, if we take the derivative of, so the first term, we get dy dx times x cubed is this term here. And then if we take the derivative of the second term, x cubed, which will give us 3x squared. So 3x squared times the first term, y. So the product rule just says that the derivative of the product is equal to one term times the derivative of the other term plus the derivative of the other term times the other times the original term. So that's times the first term. So whatever order we take, it doesn't matter. But here we've got the derivative of y with respect to x times this plus the derivative of this term here times y. You can see this is equal to this by the product rule. Okay, so that is equal to that, which is equal to x cubed times cos of x. Okay. So now we can just integrate both sides with respect to x. Now we might have also been given an initial condition. So we might have had this differential equation, and perhaps we've also been given an initial condition. Say at x equals 0, y equals 4. Okay. So I'll use that condition when I integrate. So I'll integrate dx of y times x cubed with respect to x from 0 to x. Now we know what y is at x equals 0. We've been given that at x equals 0, y equals 4. So that's why I chose to integrate from 0 to arbitrary x. Okay, so that will equal the integral again from 0 to x cubed cos of x dx. This gives us, now by the fundamental theorem of calculus, the integral of the derivative is whatever we took the derivative of in the first place. So we'll just get y x cubed evaluated at x minus y x cubed evaluated at 0 equals, so we've got some definite integral on the right hand side, and this can be solved using integration by parts. So this integral on the right hand side can be solved using integration by parts. If we evaluate this expression at x equals 0, well, we'll just get 0 times sine of 0, so we get 0 times 0, which is 0. This should have had x 0 there. So we're integrating this from 0 to x. We'll have to again use integration by parts to solve this integral here. So after repeated use of integration by parts, we end up with yx cubed evaluated x minus yx cubed evaluated at 0 will equal this expression here. So I'll just write out the left hand side. So y times x cubed minus, now y evaluated at 0 is 4. So 4 times 0 cubed. So this term here is just going to be 0. It's just going to vanish. So we'll end up with y times x cubed equals this expression on the right here. So we might as well divide through by, or we need to divide through by x cubed to get y. So that will be y equals sine of x plus 3 over x cos of x minus 6 over x squared plus 6 over x cubed cos of x minus 6 over x cubed. So that's our solution to the initial value problem involving this differential equation and this initial condition. So you'll notice that we didn't need to first find a solution to the differential equation and then substitute back in the initial condition, because this method enables us to do it together in one hit. So we don't have any unknown constants here, because we've integrated through with respect to x evaluated at 0, which was the value given in our initial condition, and at x. So at x equals 0, we knew that y equals 4, and at x equals x, or y equals y. So that gave us our solution there, without some unknown constant that we needed to substitute the initial condition into. So we've got our solution to the initial value problem. I'll consider another example of an initial value problem involving a first order linear differential equation. So the differential equation will be dy dx plus x squared y equals 2x squared plus 7x plus 11. So again, we take an antiderivative of the function of x in front of y. So an antiderivative is x cubed over 3. Our integrating factor will be e to the power of this antiderivative, e to the power x cubed over 3. That's our integrating factor. So we just again multiply. I haven't given the initial condition in this initial value problem. So the initial condition will be at x equals 0, y equals 8. Okay. So multiplying both sides of this differential equation by the integrating factor gives e to the x cubed over 3 dy dx plus e to the x cubed over 3 times x squared y equals 2x squared plus 7x plus 11, all multiplied by e to the x cubed over 3. So now, as before, we can take this side and it will be equal to the derivative with respect to x of y times the integrating factor. So this equals the right hand side. So now we take the integral with respect to x from, now we had an initial condition at x equals 0, y equals 8. So we'll take the integral from x equals 0 Now again, by the fundamental theorem of calculus, the integral, the definite integral of this derivative will just be this function with which the derivative is taken. So in other words, y equals y times e to the, y to the times e to the power x cubed over 3. Evaluated at x minus the same thing evaluated at 0. And then we also have to solve this integral as well, which can be solved using integration by parts. I'll consider another example of an initial value problem involving a first order linear differential equation, and I'll again solve it using the integrating factor method. So the first order linear differential equation will be of the form, or can be written of the form, as in the form dy dx plus f of x, so some function of x times y equals some function of x. Okay, so in this case I'm going to choose the differential equation dy dx plus x squared y equals 2x squared. And the initial condition will be at x equals 0, y equals 8. Okay, so again we find the initial, the integrating factor by taking the exponential of this function of x in front of the y. Of an antiderivative rather of that function of x in front of the y. So this function here in front of x in front of the y, this function here is x squared. So we take an antiderivative x cubed over 3, and we take the exponential of that antiderivative, and that's our integrating factor. So that's our integrating factor. Okay, so now we multiply both sides of our differential equation by our integrating factor, e to the power x cubed over 3 times dy dx plus x squared e x cubed over 3 times y equals 2x squared times e to the x cubed over 3. Now, we will again get that the derivative with respect to x of y times the integrating factor will be identical to this expression here on the left. And that can be checked using the product rule. If you take the derivative of this expression here, you'll find that it will be equal to that expression there. Okay, so using the fundamental theorem of calculus, or rather, actually we haven't got to that fundamental theorem yet, but we'll take the integral of both sides, respect to x, and now this definite integral will be evaluated, and we have to take both sides, but the definite integral will be evaluated from 0, from x equals 0, because that's the value involved in our initial condition. So again, we take the integral from 0 to x of both sides, so that's 2x squared times e to the x cubed over 3 dx. Now again, as I was about to mention, we'll use the fundamental theorem of calculus. So what that means is that integral of the derivative of a function will just be the function itself, and because this is a definite integral here, it'll actually be the function itself evaluated at the upper terminal minus, so this function itself that we're taking the derivative of and then we're integrating with respect to, we take this function evaluated at x minus this function here, y to the power x cubed over 3 evaluated at x equals 0. Okay, so that is equal to this integral over here. So this term, this expression here can be evaluated. We just plug in x and 0. Now at x, when x is x, y is just y, so that's y e the x cubed over 3. When x is 0, y is 8. So we have 8 e to the power 0 cubed over 3. Okay, now this e to the power 0 cubed over 3 will just be e to the power 0, which is just 1. So we'll have ye times x cubed over 3, take 8 times 1. Now the right hand side can be solved using a u substitution where we take, okay, so we'll let u equal to x cubed over 3, and then the derivative of that with respect to x will be x squared. So we'll end up with 2 times du dx times e to the power u. See, we've set u to equal x cubed over 3 dx. So now we've got ye to the x cubed over 3 take 8, because this is just 8 times e to the power 0, which is 1, so it's just take 8 equals, now we can pull the factor of 2 out of the integral, and we can also, because we've got du dx and dx here, we can just change this to an integral with respect to u, but we need to change the terminals. So at x equals 0, right, we need to work out what u is equal to, well, if we substitute 0 into here, we'll just get 0 into here for x, we'll just get u equals 0. X equals 0, u equals 0. So we can, that's u equals 0, and at x equals, well, when x is x, well, u is whatever value u is, and a value of x. So I've just got this e to the u term within the integral. So e to the u, the integral of that will just be e to the u itself. So we've got 2 times e to the u evaluated at u and 0. That's t2 times e to the u minus 2 times e to the 0. Now, u is x cubed over 3, so I'll put that back in. 2e to the power x cubed over 3, take 2 times e to the 0 is 1, so I'll just take 2. And then we have, and of course this is all equal to y times e to the x cubed over 3, take 8. So some further rearrangements will give 2e to the x cubed over 3, add 8 to both sides, and we get plus 6. So then we end up with y equals, dividing through by the e to the x cubed over 3, we get, so that will cancel out here, and we'll just get 2 plus 6e to the negative x cubed over 3. So that's our solution to this initial value problem here with this differential equation and this initial condition. Y equals 2 plus 6 times e to the negative x cubed over 3. I'll do one more example of an initial value problem involving a first order linear differential equation. So again, a first order differential equation can be written in the form dy dx plus some function of x times y equals another function of x. Okay, so this time I'll use the differential equation. I'll consider the differential equation dy dx plus 6y equals 7x plus 11. So you can see that the function of x here is actually just a constant. It doesn't vary with respect to x, it's just 6. This function, this f of x, that is. So our integrating factor will be e to the power of some antiderivative of this function of x, this constant. Well, an antiderivative of 6 is 6x. So the integrating factor is e to the power 6x. So multiplying both sides of this equation, I'll have the initial condition at x equals 0, y equals 5. So multiplying through by this integrating factor, we get e to the 6x times dy dx plus e to the 6x times 6y equals e to the 6x times 7x plus 11. And now again, this expression here on the left is identical to ddx of y times e to the 6x. And again, you can check that for yourself. So this is equal to this expression on the right. I'll just write this around the other way. 7x plus 11 times e to the 6x. And now we can take the integral of both sides and we'll integrate from 0 to x, because we've got an initial condition involving x being 0. At x is 0, y is 5. So we'll take the integral from x equals 0 to x. Now again, by the fundamental theorem of calculus, we'll get this integral here will be equal to this expression here that we've taken the derivative of, this y times e to the 6x, evaluated at the upper terminal, minus this expression evaluated at the lower terminal. So that's equal to this integral here, which I can solve by integration by parts. I missed those terminals there, so I'll put them back in there. Oh. And this will come to 1 over 6, 7 plus 11 e to the 6x minus 11 over 6 minus 7 over 36 e to the 6x plus 7 over 36 e to the 0. So this gives us that we can also evaluate the left-hand side as well. So that will be, well, at x equals 0, y is 5. So we got 5 e to the 0. Oh, we've got y e to the 6x minus 5 e to the 0. And then we can simplify this and this expression. Both the left and right hand side can be simplified. So we'll get y e to the 6x take 5 equals 1 over 6, 7x plus 11 e to the 6x minus 11 over 6 minus 7 over 36 e to the 6x plus 7 over 36. Now we can add 5 to both sides, so we don't have this 5 here anymore, we won't have this 5 here anymore. So that will give us y e to the 6x equals, and then that 5 minus 11 over 6 plus 7 over 36 will give us 121 over 36 when we add them all together, all these constants, these three constants. And then that we have this term here, plus 1 over 6, 7x plus 11 times e to the 6x, take 7 over 36 e to the 6x. Now we need to divide through by this e to the 6 term, so we just get y on itself. This implies that y equals 121 over 36 e to the negative 6x plus, now we divide these two terms also by e to the 6x, so that cancels out these e to the 6's. So we'll just have 1 over 6, 7x plus 11 minus 7 over 36. Oh, and we also have this 11 divided by this 6 and this negative 7 over 36. That gives us actually another constant term which we can actually simplify further. Then this expression for y can be simplified further to 1 over 21 over 36 e to the negative 6x plus 7 over 6x plus 59 over 36. So that's our expression for y. That's our solution to the initial value problem involving this differential equation and this initial condition. Y equals 121 over 36 times e to the negative 6x plus 7 over 6x plus 59 over 36. So in the past few videos, we've gone over first order differential equations. In the next video, I'll be moving on to second order differential equations.